In this next lesson, what we're going to look at is still friction on a slope, but this time we're going to look at scenarios that are called dynamics problems, so where the object is actually accelerating. The approach is exactly the same, but it's just that the object is actually accelerating in these scenarios, which makes it a little bit more complicated, but not by much. So a particle is held at rest on a rough plane, which is inclined to the horizontal at angle alpha, where tan alpha equals 0.75, or 3/4. The coefficient of friction between the particle and the plane is 0.5. The particle is then released and it slides down the plane. We've got to find out what the acceleration is and how far does it slide in 2 seconds. So the first thing we're going to do is just draw a plane. And then we're just going to put all of the information on. So we've got a particle, so let's just draw as a box, and it's inclined at angle alpha. Now, dealing with this bit here, tan alpha equals 0.75. We've done this before when we did inclined planes in chapter 5. Tan alpha is 3/4. So that means that opposite over adjacent is 3/4. So the opposite is 3, and the adjacent is 4. Using Pythagoras, that means that the hypotenuse is 5. It then means that sine alpha, which is opposite over hypotenuse, is 3/5. And cos alpha is 4/5, adjacent over hypotenuse. And these values are much more accurate to then use. The coefficient is 0.5, so mu is 0.5. Now, we've got to work out everything else, basically. It doesn't tell us the mass, but you might remember that when we did slopes before, it didn't actually matter what the mass was in particular. So we can put the weight on. So we've got mg. Resolve this. This is angle alpha. So we've then got mg cos alpha. And we've got mg sine alpha. We could put the directions on too. We've also got r. And if it's sliding down the slope, which it says that it is, we can label A as being down that way. If it's accelerating down the slope, then that means that friction must be trying to stop it and going that way. Now we can do our resolving. So let's do perpendicular to the plane first of all. R must equal mg cos alpha. Or I could write that as 4/5 mg. Now I can resolve down the plane. So I've got mg sine alpha, is pulling it down. The force trying to stop it is obviously friction, so that's going to be minus mu r. So that's minus 0.5, so mu times r, which is 4/5 mg. And that equals ma. Like that. In all the problems we did the last couple of lessons, it's always been equal to 0 because it's been in equilibrium, but now it's accelerating, so we can just equate it to ma. Now at this point you can see why it doesn't matter that we're not given the mass. We can divide everything through by m. So we've just got g sine alpha. Sine alpha was 3/5, so it's going to be g, or 3/5 g, minus 2/5 g, because 0.5 times 4/5, equals a. So that's going to be 1/5 g equals a. And we can work that out as a number. 9.8 divided by 5, so 1.96 meters per second squared. Now part B. The distance it travels in 2 seconds. So this is basically a SUVAT problem, assuming that it's constant acceleration. The initial speed was 0 because it said it was released from rest. We want to find the distance. The acceleration we now know is 1.96, and the time is 2 seconds. So that's going to be s equals ut plus half at squared. So you get 3.92 meters. Is our answer there. So you can see the skills in these problems are exactly the same, it's just that it happens to be accelerating. Okay, here's another one. I'm just going to draw the diagram for this. So this time we've got a box of mass 2 kilograms. Let's draw that on. Is pushed up a rough plane by a horizontal force. So it's not a force parallel to the plane, it's a horizontal force. So it comes in like this, of magnitude 25 newtons. The plane is inclined to the horizontal at an angle of 10 degrees. So that also means that that angle there must be 10 degrees, because it's an alternate angle. Given that the coefficient of friction is 0.3, find the acceleration of the box. Now it says it's pushed up the plane, so we can assume that it is actually going up the plane. And now we've got to do all the usual things we do. So let's put the weight on and resolve it. So we've got 2g cos 60, 2g sine 60. We've got r. We can resolve the 25. Maybe let's do this in a different colour actually. Got the 25, so that's a force that way and a force up the slope. So this is 25 sine 10 and 25 cos 10 up the slope. Now the last thing to think about is friction. If it's accelerating up the slope, then friction must be trying to slow it down. So friction is going down the slope. There we go. So we've got all of the workings done on here already. Now let's see what we can do in terms of resolving. So let's go perpendicular to the slope first of all, because then we can find r and then we can find friction. So I've got r. That must be equal to 25 sine 10 plus 2g cos 60. Just because I've got this force going in that direction, and then I've got that one and that one going the other direction. So r must be the same as this plus this, because perpendicular to the slope, it's not accelerating. It's accelerating up the slope, but in this direction, it's not accelerating. You could write r minus 25 sine 10 minus 2g cos 60 equals 0 if you preferred. But now we've got this, we can work out what r is. So that gives me a value for r of 14.14. And now we can resolve up the slope. So force going up the slope is 25 cos 10. Force is trying to stop it, so it's going to be minus 2g sine 60. That's the component of the weight here. And also minus friction, so it's going to be minus mu r. So that's minus 0.3, which was mu, times r, which is 14.14. And that equals ma, so 2a. And then we can solve this to find what a is. So 25 cos 10 minus 2g times sine 60 minus 0.3 times 14.14. That's 2a, so divided by 2. About 1.7 meters per second squared. Okay. Before we have a go at some questions, just want you to remember about what we talked about last lesson, about things when they're on the point of slipping. If it's on the point of sliding down, so the box wants to move down, that means that friction must be acting up. Okay, so it wants to slide down, so friction must be acting up. It's on the point of sliding up, so it wants to move up, so friction must be acting downwards, like this. And we discussed how this force of P here would need to be much bigger because of that. Because here friction is helping you, and here you're trying to work against friction, essentially. So some of the questions do touch on that again. Now, there's two tasks I want you to do. The first one is just a short worksheet on inclined planes of friction, like we've just been doing. There is some answers at the bottom of it. So it looks like this. So there's 6 questions, and then the answers are just at the bottom there. Okay. Now the other sheet that I want you to have a go at, which is a bit longer, it's just called Slopes of Friction Mastery Sheet. Now this is a sheet that I made myself to try and get students to practice basically all of the different scenarios that could happen with friction and a slope. So it starts off pretty easy, but gradually it gets more complicated. So there's extra forces, forces at angles, forces at slightly more difficult angles, different things to work out. Okay, but I've also given you, well, there's the answers at the end, but you've also got the worked solutions here as well with my handwriting solutions on. So please use those to help you if you get stuck. If you can do all of those, then you can pretty much handle anything that they will throw at you.